Okay, let's pick up the pace a bit now and start implementing some of this. Networking. Networking, right. You need your two physical networks, public network, private network. If you're using release 12 flex clusters, you also have what they call an ASM network. That's usually, however, logically on top, that's usually only a logical network on top of an existing private network, but it could be physically separate. But usually that's just a logically separate network. And you can have many more if you want. Now, I said I'd come back to multiple network cards such as ODA, the bonding concept. Let's assume that instead of having just one interconnect, like an ODA, we've got two InfiniBands. Let's assume that instead of having one public network, we've actually got two public networks. And remember, the ODA, you've got multiple 10 gigahertz network cards for that. How do you handle multiple network cards? Well, best practice is for the private network, you don't do anything at the operating system level. You let Oracle see both. But for the public network, Oracle best practice is to bond the two together. So you don't expose both network cards to Oracle. You bond them. Right, how do you do that? You've just got time to see that, I think. I'll show you how it's done, because you need to be aware of this for your own environments and your own hardware, how actually to do it. So I'll take just a couple of minutes showing you how it's done. On this machine here, Paris 1 it's called, I have config. I've got one network card, ETH0, and there's its address. I happen to know there are actually 4 network cards in this machine. I happen to know there are 4. So what I need to do is enable what we call bonding on, say, 2 of them, bonded down to 1. How do I do that? Right, it's very simple. Your system administrators will be doing this, of course, but technically we know how to do it, because we may be configuring the whole cluster ourselves. And it's pretty straightforward. Now, what we would do is, let's see, what's the easiest way going to be to do this? Yes, we'll start by creating what we call a bonded network. There will be variations here depending on your operating system. You know, Solaris is a bit different from Linux, Linux is a bit different from Windows, but conceptually it's always like this. We load the bonding module under Linux, mod probe, maybe loaded already, mod probed, bonding, load the bonding module, and specify a mode for bonding. I'll come back to mode in a second. Get your bonding module loaded, using whatever is specific to your platform. Then you have to create a virtual interface card. I have config, and I'll call it bond0. You normally call it bond0. ODA calls it bond0. An ODA of bond0 and bond1. But bond0, and I'm going to make its hardware look like an Ethernet card, and you give it a MAC address. And there's a range of MAC addresses you're meant to use for private networks, or privately organized ones. That's its MAC address. Done. Then give it an IP address. I have config, bond0, and I'll give it an IP address, so 192.168. Dot, what am I on? 56 dot, I don't know, 199. And bring it up bond0. That's creating a network card. But then the clever bit, the bonding itself. I have config, and what I shall do is use the ifnslave command. ifnslave. Again, there may be slight syntactical variations depending on your platform, but I'll put ETH1 under the control of bond0. And I'll also put ETH2 under control of it. Ooh, it's already a slave. Let's try ETH4. No such device, ETH3. Enslave, oh, it's already a slave. Okay. 2. Enslave failed. Okay, let me do it differently. I have config, maybe it's already there. I have config. I've got ETH1 running slave. Okay. Maybe I can enslave ETH0 as well. Will that be a disastrous problem? Let me enslave ETH0. I'll reboot after doing this to make sure it's okay afterwards. Enslave that. Oh, there we go. And then I have config. Right. So I've got ETH0 and ETH1 enslaved to bond 0. And you can see what's happening. The network traffic. Bond 0 has received 9,000 packets, of which 8,600 went to ETH0, and the remaining 292 went through ETH1. That's because that was running out of slave mode earlier, which is why it's so much higher. So whenever I ping my bond 0 address, which is that, if I ping that, which is the virtual network card, the traffic is in fact being load balanced across the 2 network cards that are enslaved to it. And that's what you will do. That's done for you on ODA. That's done for you automatically when you do your initial configuration. If you're building your own, if you're rolling your own environment, you will have to decide how to do this. Generally speaking, what Oracle recommends is, I'm just going to get that out of the way. What Oracle normally recommends is that for the public network, you bond your network cards. So you bond these 2 into 1. And for the private network, you leave them unbonded and exposed to grid infrastructure. The idea is the grid infrastructure has got their GI both sides. So Oracle can do its own load balancing and fault tolerance across the private network. For the public network, we don't know what's the other side. So it's better to use the operating system bonding facility to combine those 2 into 1. That's the general rule. Okay, now, what I shall do next, just want to...
John, is the bonding taken care of for you in ODA?
Yes, it is. They may want to adjust it. You may want to adjust it later. But the standard configuration through the wizards, you'll find you've got bond 0 and bond 1. And bond 0 is 2 of your 4 10 gigahertz cards, and bond 1 is the other 2. So it should be done for you. You might want to adjust it, but it's meant to be done for you. Okay, now I'm just going to, oops, give me a moment. Right, so that's the networking. I've talked about the cluster connects and the networks you might have available. The cluster interconnect is your private network. It will have fixed addresses resolved by DNS and virtual addresses assigned by HAIP. HAIP is Oracle's High Availability Interconnect Protocol. If you look at my node here, cat etc hosts, you'll see that I'm running on machine Berlin 1, and Berlin 1 has a network card address 31, and it's got Berlin 1 priv 10.11.31. That's my private network. That's my public network. Now the fixed addresses will be resolved by DNS, but then Oracle itself assigns HAIP addresses, ifconfig. If we look at my /sbin/ifconfig. Right, ETH1 is my private network. There's that address, 10.11.31, which can be resolved through my host file, 10.11.31. Berlin 1-priv. But there's another address on it, a 169 address. That's a virtual IP address created for us by grid infrastructure. And every interconnect network will have one of them. Oracle manages it, starts and stops it, the multicasting going on, keeps it highly available. And Oracle itself can load balance between them. And that's why they say don't bond them. Let Oracle do it instead. If you've got 8 interconnects, well, HAIP can only handle 4, up to 4. So if you've actually got 8 interconnects, then you will need bonding to bond the 8 down to 4. But otherwise, let Oracle do it. Now, I just want to check my... See if that machine has come up okay. /sbin/config. Right, I think I'm back to normal. Hope I'm back to normal. Okay. Now, public IP addresses. The public IP addresses are the addresses you're going to expose to the outside world. So they are, if I get my diagram, they are the addresses that your application servers will be using to connect through one bonded address, probably, to the database instances. Those are the public addresses. Now, you have one virtual IP address per node by default, but you can add more because the VIPs can move around the cluster. Then you have scan VIP, single client access names. Well, look at what's going on here. If you look at my node Berlin 1, there's ETH0, there's its fixed static address. But we've got 1, 2, 3, 4, another 4 virtual IP addresses have been started. One of them will be the VIP, the other will be what we call the scan VIPs. And if you're using grid plug and play, which I am, a fourth one will be the grid plug and play address. So there's quite a lot going on here in terms of IP addresses. If I look at my other node, Berlin 2, SSH Berlin 2, oops, the other node in my cluster, ifconfig /sbin/if config. There's the interconnect with its HIP address, and it's only got one virtual address. Well, no, sorry, it's got two virtual addresses running on its public network. So what are these things? Well, you have one VIP per node and 3 scans by default. And what's the scan? Single client access name. SRVCTL config scan. The single client access name on my cluster is Berlin-scan Europe example.com. And it's got 3 IP addresses. 192.168.56.138, 154, 152. So if I ping it, ping -C1, Berlin scan, I've gone to 138, 192.168.56.138. Ping it again, I've gone to 154. Ping it a third time, I've gone to 152. Ping it a fourth time, and back to 138. So by default, you have 3 scan VIPs, 1 scan name, single client access name, mapped to 3 addresses. That's the beginnings of your fault tolerance. As long as even one of those 3 addresses is working, people can connect to your databases. But there may be more as well. Name resolution, come to us in a second. So that was the scan, a stable name used for cluster services, a single point of entry to the cluster. There's a 2-tier listening architecture, which we have to become familiar with. So I'm going to attempt to draw another diagram. Let me get rid of that one. And create, don't think I need to save that, do I? Open a new diagram. Nope. And I'll sketch out the 2-tier listening architecture. Node listeners and scan listeners. I'm going to sketch here, let us assume that we have a 4-node cluster. A 4-node cluster, to make it a larger, bigger example. So I've got a node here, node 1, node 2, node 3, node 4. And they are all, of course, connected through the interconnect, and they're all connected to the shared storage. So 4-node cluster. Now, we have on each node, we run what we call a node listener. Node listener 1, node listener 2, node listener 3, node listener 4, NL1, 2, 3, 4. 4 node listeners. Then we have 3 scan listeners. Scan listener 1, scan listener 2, scan listener 3. We have 3 scan listeners. Now, what addresses are these things listening on? Well, the node listeners listen on the node's virtual IP addresses. The scan listeners will each listen on 1 of the scan addresses. As I demonstrated, by default, you have 3. There they are. So, why do we have this 2-tier listening architecture? Well, imagine the user and what he's going to do. Your user up here, here I am, running SQL+, and I say, connect Scott Tiger at, and I give it the scan name, port 1521, and I ask for my database service, JW perhaps. Well, what's going to happen when I do that? Let's do it and see. Oops, check W. Right, that's my scan name, my single client access name. So SQL plus system/Oracle at. Now I'll go to the scan, Berlin scan. Oops. Go to the scan name, and I have no idea physically what that means at this point. My user has port 1521, and ask for the service JW. Need to change the password, apparently. Okay. Right. There we go. So what happened when I issued that command? SQL plus system Oracle at Berlin scan. You saw when I pinged Berlin scan 3 times, each of my ping requests was directed to a different scan listener. That's the DNS load balancing. DNS will randomly send me to one of the scan listeners. Maybe it sends me to that one. What happens next? The scan listener intelligently redirects me to a node listener. It's a redirection. A redirection request instruction goes back saying, go there. That's what scan listeners do. They are the entry point to the cluster. They receive all logon requests, and they redirect you to an appropriate node listener. What's an appropriate listener? One that is servicing local instances that are offering the application you want to connect to. This is a 4-node cluster. There might be 10 databases on it. Some of the databases might be single instance. Some of them might be 4 instance. There could be anything running on that. The scan listener knows where to send you. And if node 2 here dies, it'll redirect you to a different one. That's the 2-tier listening architecture. Node listeners, 1 per node. Their purpose is spawn and bequeath of sessions. So my node listener receives the request, it launches a server process, and there I am logged on. You get the socket transfer. Yep.
Do you have to use a scan? Can you contact a node directly?
You can contact a node listener directly, and you may have to. You may have to. If you've got really old client software, perhaps that can't understand things like redirection requests, then you'll have to contact the node listener directly. To put it another way, the code hasn't branched. The code has not branched. So you don't have to use the 2-tier structure. I think that may change in the next release of the database. Because ideally, the scan listeners have one function only, which is redirection, high availability, and load balancing. And the node listeners, their function is spawn and bequeath. So logically, they're completely separate. But yes, they can actually both do both jobs. Backward compatibility. That's your 2-tier listening architecture. All your end users ever know is the scan name. They don't know whether behind that scan is a 4-node cluster or single instance database. They have no idea at all. Final topic, I think. Almost the final topic. Yeah, almost the final topic before break time. The grid naming service. The grid naming service. How do you handle name resolution? Well, you've got options for whether to use DHCP addresses or not. In my cluster here, I'm actually using DHCP. Every time I boot up the machine, I might be picking up different virtual IP addresses. So basically, on this node here, Berlin 2, I've got 2 virtual IP addresses. Let's look at the listeners. And we'll see what's actually running on this thing. PS-EF pipe grep TNS. There are in fact 3 listeners running on this machine. The ASM listener I'm not going to talk about. That's to do with Flex ASM. We don't have time to talk about that now. But listener scan 1 and the node listener. Whereas if we look at my other node, PS-EF grep TNS, this is running a total of 4 listeners. The ASM network listener I'm not going to talk about. The node listener, and 2 scan listeners. By default, you have 3 scan listeners, which is a bit stupid on a 2-node cluster. But the scan listeners will relocate and distribute themselves across the cluster. They can't really do that on a 2-node cluster. And if we look at those things, well, lsnrctl status listener, we find that my node listener on Berlin 2, the node listener knows about, oops, that's NRCTL, status listener. The node listener knows about the JW database instance, the JW database service, I should say, and the JW2 instance, because that's the instance running on this machine. SLVCTL, status database, minus DB, JW. JW2 right now has JW1 on Berlin 1, JW2 on Berlin 1, 2. And that's all the node listener knows about. Looking at the other one, the other node, it's got symmetrical information. It knows about JW, the database, and the service. Oh, so JW2 is on Berlin 2, JW1 is on Berlin 1. But what about the scan? Well, let's check the status of listener scan 1. Listener scan 1, well, I never. It knows about both instances. And that's the heart of the redirection mechanism. The scan listeners know about the entire environment and can redirect you appropriately. What about names, though? How do we do name resolution? Well, that's a matter of whether you want a view and your system administrators. If you're using DHCP, which is what they call grid plug and play, then all the IP addresses are assigned by a DHCP server, and in that case, DHCP server, and in that case, Oracle has to do the name resolution. Or alternatively, you can statically register your VIPs in your DNS. It's entirely up to you whether you use grid naming service. It allows use of DHCP. I like to use it myself. It's not that widely used, but people who do use it are usually very happy. Most people, yeah, grid plug and play, DNS plus DHCP. It's DHCP to assign the names, and then GNS works with it. If you can't use DHCP for some reason, you just statically register everything in DNS. In our class, by the way, we go through how to configure the DNS for all of this. And then the final topic, flex clusters. Everything so far has been about building the cluster and getting it ready for databases. In 12c, Oracle introduces the concept of the flex cluster. This is really Uncle Oracle takes over the world. Grid infrastructure becomes general purpose clusterware. And the idea is that you bring all your servers into the cluster, not just your database server. You have two types of node. Hub nodes run databases, leaf nodes run applications. So you might well have, say, 4 database servers in your cluster, 8 application servers in your cluster. 8 leaves, 4 hubs. And that allows grid infrastructure to give you full fault tolerance for your applications. So your mail server can fail over from one machine to another, all managed by grid infrastructure. And the virtual address, smtp.skillbuilders.com or whatever, will relocate with the mail server process. It's a declarative technique where you simply tell grid infrastructure, I would like this database to have 3 instances and this database to have 2 instances, but I don't care where. Let grid infrastructure sort it out. You tell grid infrastructure, I want my Apache web listener to be running on at least 2 nodes. And if one of them fails, relocate the one that fails to another node. Your Tomcat servers, again, tell grid infrastructure which machines it's allowed to start them on, and let grid infrastructure work it out. A very powerful declarative technique for high availability and performance levels for applications as well as databases. And that concludes our architectural summary. And in the rest of the week, we go through it all in horrendous detail. The takeaways here, you've got layers of clustering, and each layer has to be complete and functioning before you proceed to building the next. You need a thorough understanding of IP addresses, the differences between fixed and virtual addresses, static and dynamic addresses. How are you going to do name resolution? And the 2-tier listening model, scan listeners and node listeners. If this were our class, you would then do your first major exercise as you get your nodes ready for doing the installation. Back to you, Dave.
Thanks, John. Yeah, so if this were the class, you know, we do a lot of hands-on. You get an opportunity to build each one of the constructs in the architecture. And of course, John is available to help you in case you have some problems. So what we're going to do now is take a short intermission. We'll take a 10-minute break. It's half past the hour, 12:30 where I am. And we'll take 10 minutes, 12:40, and then we will reconvene at 12:40 with a demonstration.
I must say, with regard to the consulting work, we do a lot of consulting work, and we're not really interested in doing your sort of everyday database admin. So any jobs we do, we always do the skills transfer so that we can hand over afterwards. Now, what I'm going to do now is jump straight into much later in the course, where we actually create RAC databases. But I don't want just to create one. I want to do what most of you will be doing, which is converting the existing database into RAC. Before diving into it, I have to do one very quick bit of theory. I promise this is the last horrible diagram I'm going to draw. In a clustered environment, you have the concepts of, oops, let me get the right pen, right. I'm going to draw this as an entity relationship diagram. Like all DBAs, I'm infatuated with normalization. I would normalize humans if I could. In the RAC environment, you've got one database, but the database is opened by multiple instances. That's what RAC is all about. One database, multiple instances. To convert to RAC, there's slight physical change. There are two physical changes. Within the database, you have to create multiple undo table spaces. So multiple undo table spaces in the database, and each undo table space is used by exactly one instance. So if you've got 4 instances, you create 4 undo table spaces. Also within the database, you create multiple threads of redo. The concept of a thread of redo. A thread of redo. Within the database, multiple threads get created, and each instance mounts exactly one thread. So if you've got a 2-node cluster, I would normally create 3 undo table spaces and 3 threads, so there's a spare, just in case. Each thread of redo consists of multiple online log file groups. I'm sure we all know that you must have at least 2 groups. So if it's a 2-node cluster, you'll need at least 2 threads, and each thread will have at least 2 groups. And each group, of course, is meant to consist of multiple online log file members. So that's the structure we've got to set up. The database on shared storage with its multiple threads, its multiple undo table spaces, and then the instances existing, or the processes and memory structures existing on each node.